There's a sentence sitting inside a Google research paper that most people have not read, and the people who have read it are not entirely sure how to feel about it. It says that a chip the size of a coin may have just proven that you're not the only version of yourself in existence. Not metaphorically, not as a thought experiment, as a possible scientific implication of a working machine. Read that again. A machine built in a lab in Santa Barbara did something so strange that the man who built it stood up and said it lends support to the idea that we live inside a multiverse. And here's the part that should genuinely unsettle you. Nobody at Google has denied it. They have only tried to manage how loudly it gets said out loud. This is not a story about a faster computer. Faster computers get announced every year and nobody loses sleep over them. This is a story about a machine that did something in under 5 minutes that the fastest supercomputer on planet Earth would need 10 septillion years to do. 10 septillion. That number does not fit into a human brain the normal way, so let it sit for a second. 10 septillion years is longer than the universe has existed, multiplied by itself, multiplied again. And Google did not just claim this quietly in a press release. They published it in Nature, the most scrutinized scientific journal on the planet, daring the entire physics community to prove them wrong. Nobody has. What most people are not seeing is that this announcement did not happen in isolation. It happened at the exact moment 3 other global powers were racing toward the same finish line in near silence. China's National Quantum Lab had just unveiled a portable quantum prototype. IBM was quietly expanding its own cloud-accessible quantum fleet. Microsoft was repositioning its entire Azure quantum strategy. And, in the middle of all of it, Google detonated a result that did not just outperform its rivals. It appeared to outperform the laws of probability that this kind of result should even be possible this early. According to informed industry observers, the timeline that quantum scientists had quietly agreed on just 2 years earlier, we are still several years from quantum advantage, collapsed overnight. Not gradually, overnight. To understand why this matters, you need to understand what Google actually built, because the name Willow sounds almost deliberately soft for something this aggressive. Willow is a 105-qubit superconducting processor manufactured in a dedicated Google campus in Santa Barbara, California, a facility most of the public has never heard of, and few journalists have ever been allowed inside. It was first revealed in December 2024, and even then, it carried a claim that sounded almost too clean to be true. Willow could reduce computational errors as it scaled up, instead of accumulating them the way every previous quantum machine in history had. This is not a minor technical footnote. This is the single problem that had blocked quantum computing from becoming real for almost 30 years. Here is where it gets worse for anyone trying to dismiss this as hype. Quantum computers are built on qubits, the quantum version of a regular computer bit. But qubits are notoriously unstable. They lose their information almost the instant you try to use them, like trying to hold smoke in your hands. For decades, the assumption inside the entire field was brutally simple. The more qubits you add to scale up a quantum machine, the more errors you generate. And eventually, those errors drown out anything useful the machine could ever calculate. Every quantum computer ever built had obeyed that rule. Willow broke it. Google's engineers demonstrated something called below-threshold error correction, proof that as they added more qubits to the system, the error rate did not rise. It fell exponentially. Think about what that means. The thing that was supposed to make quantum computing impossible at scale just became the thing that makes it scalable. But the December 2024 announcement was only the opening move. The real detonation came almost a year later, in October 2025, when Google published something called the Quantum Echoes algorithm. And this is the part of the story most people still have not caught up to. Quantum Echoes was not just fast, it was verifiable. That single word, verifiable, is the difference between a magic trick and a scientific fact. Earlier claims of quantum supremacy, including Google's own 2019 Sycamore experiment, had been criticized for years because the problems being solved were essentially designed to be impossible for classical computers, with no real-world use and no independent way to confirm the answer was even correct. Critics called it computational theater. Quantum Echoes was different. It ran an algorithm measuring something called out-of-time order correlators, a way of tracking how a disturbance spreads through a quantum system over time, and it did it 13,000 times faster than the best classical supercomputer alive. And because the result could be repeated and cross-checked on a separate quantum device, scientists outside Google could not simply wave it away as a black box. This is not chaos. This is strategy. Google did not stumble into this milestone. They built toward it across 6 deliberate stages, what insiders call the roadmap. Starting with a 2019 Beyond Classical demonstration, moving through a 2023 logical qubit prototype, then the 2024 below-threshold breakthrough, and now the 2025 verifiable advantage. 4 milestones down, 2 left, And the next milestone on that roadmap is not a research curiosity. It is a fully error-corrected, large-scale quantum machine, something Google's own CEO Sundar Pichai has internally framed around the year 2029, 3 years from now. Think about what kind of institution plans a multi-decade scientific assault on the laws of computation and hits every single internal deadline along the way. Now, here is where the story stops being about chips and starts becoming about something closer to the architecture of reality itself. Because this is where Hartmut Nevin enters the picture. Nevin is the founder of Google Quantum AI, the man who has overseen this entire roadmap since 2012. And he is not a marketing executive prone to wild exaggeration. He is one of the most credentialed quantum scientists alive. And it was Nevin, not a tabloid, not a clickbait channel, who stood in front of the results of the Willow chip and said something that should have been the lead story on every major outlet in the world. He said the success of Willow lends credence to the notion that quantum computation occurs in many parallel universes, explicitly tying the result to physicist David Deutsch's decades-old multiverse interpretation of quantum mechanics. The real story is that one of the most senior quantum scientists on Earth is now publicly entertaining, on the record, the idea that his own chip might be borrowing computational power from realities running parallel to ours. Sit with that for a moment, because most people scroll past sentences like that without absorbing what they actually imply. The multiverse interpretation of quantum mechanics is not science fiction lore invented for a movie franchise. It is one of the oldest and most seriously debated frameworks in theoretical physics, dating back to a 1957 doctoral thesis by Hugh Everett. It argues that every quantum event that has more than one possible outcome does not collapse into a single reality. It splits into multiple realities, each one playing out a different version of the event, branching endlessly, forever, with you in every single one of them, living a slightly different life each time. For most of the last 70 years, this idea lived almost entirely in academic philosophy seminars and late-night physics debates because nobody could test it. There was no experiment, no data, no way to falsify it or confirm it. Willow may be the first machine in human history whose behavior is so strange that a credible scientist is willing to say, on the record, that this once untestable theory might be leaving fingerprints in the lab. And this is where everything changes, because once you take that idea seriously, you have to ask the uncomfortable question underneath it. If a quantum computer's performance can be explained by computation happening across parallel branches of reality, what exactly is being computed there, and who or what controls access to it? Google currently does. Not the public. Not open researchers around the world. Google's quantum computing service has remained, by the company's own design, a tightly restricted preview, granting access only to a narrow set of vetted research partners, rather than the open self-service model used by its biggest rival. Compare that to IBM, which runs an open cloud where almost anyone can remotely access real quantum processors and run their own experiments. Google chose the opposite path. While its software framework, CIRC, remains open source and its published papers are public, the actual hardware, the thing capable of, according to its own founder, tapping into parallel computation, sits behind a velvet rope that only a handful of vetted institutions are allowed past. According to informed sources inside the research community, that exclusivity is not an accident of bureaucracy. It is a calculated strategic posture. Whoever controls the most advanced verified quantum hardware on Earth does not just control a faster calculator. They control the earliest access to breakthroughs in drug discovery, in materials science, and cryptography, and, this is the part that should make governments nervous, in code breaking, modern encryption, the kind protecting your bank account, your country's classified communications, and the backbone of global financial transactions, is built on mathematical problems that are nearly impossible for classical computers to solve in a human lifetime. A sufficiently powerful, sufficiently stable quantum computer does not just solve those problems faster. It can potentially solve them in a way that makes today's encryption obsolete almost instantly. This is why the US government, Chinese state labs, and intelligence agencies worldwide have been quietly funding a parallel race that almost never makes headlines. The race to build post-quantum encryption before someone else's quantum machine breaks the locks first. But here's where it gets worse, because Google did not stop building after quantum echoes. In March of 2026, only a few months ago, Google Quantum AI added an entirely new category of hardware to its arsenal: neutral atom processors, a second modality running in parallel to Willow's superconducting architecture. This was not a redundant move. Superconducting qubits, like the ones in Willow, scale beautifully in circuit depth, meaning they can run longer, more complex sequences of operations. Neutral atom systems scale differently. They handle far larger numbers of qubits more easily. By developing both simultaneously, Google effectively built two complementary weapons aimed at the same target from two different angles, covering each other's structural weaknesses on the long road toward a fully error-corrected million-qubit machine. Think about what that means strategically. This is not a company betting on one technology and hoping it pays off. This is a company hedging a multi-billion-dollar bet across two entirely separate physical approaches to the same end goal, because the prize at the end is too large to risk on a single roll of the dice. And the financial markets noticed immediately. Following the Quantum Echoes announcement in October 2025, Alphabet's market value surged as investors rapidly recalculated what verified quantum advantage actually meant for the company's future. This was not speculative meme stock enthusiasm. This was institutional capital, recognizing almost overnight that a multi-decade research bet many analysts had quietly written off as a science project was now producing reproducible, independently checkable results, with a credible 5-year runway to commercial application. Pharmaceutical companies began asking what quantum-enhanced drug discovery could mean for molecules that have resisted modeling for decades. Material science labs began asking whether next-generation battery compounds and superconductors, the kind that could reshape the entire global energy grid, might now be designable in hours instead of years. Financial institutions began quietly exploring quantum-level risk simulation, the kind of modeling that could detect economic shocks before they fully materialize. Every one of those industries is now watching a single chip in Santa Barbara the way oil traders once watched the Strait of Hormuz. What most people are not seeing is the human side of this story, and it is just as strange as the physics. The breakthrough behind Quantum Echoes was not purely a Google operation. It was built in partnership with researchers at the University of California, Berkeley, who used the technique as what scientists are calling a molecular ruler, measuring atomic distances inside molecules with a level of precision that traditional nuclear magnetic resonance technology, the backbone of modern chemistry and medical imaging, has never been able to achieve. In a proof-of-principle experiment, the team used quantum echoes to study two molecules, one with 15 atoms and another with 28, and the results matched conventional NMR data, while also revealing structural information that conventional methods could not detect. Google has compared this moment to the invention of the telescope and the microscope, instruments that did not just improve existing science, but opened entirely new categories of observation that human beings did not even know they were missing. The phrase Google's own researchers are using internally is a quantum scope, a device built to observe phenomena that have simply never been visible to humanity before. Phenomena like the internal structure of a virus, protein resisting a vaccine, phenomena like the precise atomic stress fractures inside a battery material before it fails, phenomena like, according to Google's own published commentary, the internal dynamics of black holes. Let that last one register for a moment, because it was not buried in a marketing brochure. It was stated directly by Google's own research team as a potential application of this technology, studying black holes. A machine, sitting in a research facility in California, built by a private corporation, may eventually be used to probe one of the most extreme and least understood phenomena in the entire universe, the place where the known laws of physics themselves break down. This is the same machine whose founder has already speculated in public that its computational power might be borrowed from parallel universes. The line between cutting-edge engineering and something approaching cosmology is no longer a clean line. It has started to blur, and very few people outside specialist circles have noticed how far that blur has already gone. Now, before this starts to sound like a story with no resistance, no skepticism, no counterforce, it does not. This is where the controlled reveal has to give way to the uncomfortable truth that responsible observers have been raising since the moment Willow was announced. The logical error rates Google has reported, even in this celebrated below-threshold regime, sit around 0.14% per cycle. That sounds small until you understand the scale required for genuinely transformative quantum algorithms. Error rates need to fall to somewhere around 1 in a million, several orders of magnitude lower than where Willow currently sits. Critics inside the physics community, the ones not swept up in headline excitement, have pointed out that Google's demonstrations to date have largely focused on preserving and protecting quantum information rather than running large-scale, commercially meaningful algorithms on top of it. In plain language, Google has proven it can keep the lights on longer without the building catching fire. It has not yet proven it can run an entire functioning city off that power grid. This matters because hype has burned this field before. Back in 2019, Google's earlier Sycamore chip made global headlines for what the company called quantum supremacy, a claim that was almost immediately contested by rivals, most notably IBM, who argued the same problem could, with enough cleverness, be solved on classical supercomputers in a matter of days rather than thousands of years, undermining the dramatic framing of the original announcement. Media coverage at the time was accused of wildly overstating the practical implications of a result that, while scientifically real, had essentially zero real-world application outside the narrow, artificially constructed problem it was designed to solve. Some of that same skepticism is now being aimed at Willow, and it deserves to be taken seriously rather than dismissed as noise. Quantum echoes is a stronger, more verifiable result than Sycamore ever was, but stronger is not the same as finished. Independent experts have been explicit. Willow remains for now a research prototype operating inside what the field calls the noisy intermediate-scale quantum era, still far from the fault-tolerant, large-scale performance required to deliver the world-altering applications being promised in press coverage. And this is the moment where the controlled reveal opens into the real geopolitical stakes, because none of this is happening inside a vacuum where only scientists are watching. China is not standing still while Google extends its lead. Reports throughout the last year have confirmed that China's National Quantum Lab has been racing forward on its own track, including the unveiling of a prototype designed for radically more compact deployment than anything Western labs have shown publicly. State-level investment in quantum research inside China has accelerated, specifically because Beijing understands exactly what a working, scaled quantum computer means for a nation's ability to break the encrypted communications of its rivals, and to protect its own communications from being broken in return. This is not abstract science policy. This is the foundation of a new kind of arms race, one fought not with missiles, but with qubits, where the winning side does not announce victory with an explosion. It announces victory by quietly reading everyone else's secrets while keeping its own perfectly sealed. What most people are not seeing is how close this brings the world to an encryption cliff edge that almost nobody outside intelligence circles is openly discussing. Every government on Earth currently transmits classified material, military logistics, financial transactions, and diplomatic communications protected by encryption standards built on the assumption that breaking them would take a classical computer longer than the lifespan of the universe. That assumption has been the bedrock of digital security since the dawn of the internet. A sufficiently mature, fault-tolerant quantum computer does not just weaken that assumption, it potentially erases it. And here is the truly unsettling part. Intelligence agencies do not need to wait for that fully mature machine to exist before the threat becomes real. According to a widely discussed cybersecurity strategy, adversarial states can simply harvest encrypted data now, intercept it, store it, sit on it for years, with the explicit plan of decrypting it retroactively the moment a powerful enough quantum machine comes online. Every secret transmitted today under current encryption may already be sitting in a foreign server, waiting patiently for Willow's successor or China's answer to it to finally turn the key. This is why the race toward 2029, Google's internally projected milestone for a useful, error-corrected quantum machine, is not simply a corporate roadmap. It is a countdown clock that governments around the world are watching with far more anxiety than Google's own promotional material would ever suggest. The quiet, less publicized parallel track to this entire story is the global scramble to deploy what is called post-quantum cryptography. New encryption standards specifically engineered to resist the kind of attack a mature quantum computer could unleash. Standards bodies have been racing to finalize and roll out these protections before the cliff edge arrives, fully aware that they are essentially trying to rebuild the locks on every digital door on Earth, while the thief is still several years away from finishing the master key. Whether they finish in time is, as of this moment, genuinely unknown. And here's the layer beneath the layer, the one almost nobody talking about Willow online has stopped to consider. Google's access model, narrow, restricted, vetted partners only, is not just a business decision about controlling intellectual property. In a world where quantum capability is rapidly becoming inseparable from national security capability, control over who gets to touch this hardware starts to resemble control over a strategic asset, the kind nations have historically gone to extraordinary lengths to monopolize or contain. Google did widen access slightly in January 2026 through a partnership with the United Kingdom's National Quantum Computing Center, a move that was barely covered outside specialist press, but which quietly signals something significant. Western governments are beginning to formalize direct relationships with the handful of private companies sitting on the most advanced quantum hardware on the planet, the same way governments once formed close strategic relationships with the handful of companies capable of enriching uranium or building advanced semiconductors. The pattern should look familiar, because we have lived through it before with a different technology and a different set of headlines. Think about what that means for the long arc of this story. A privately held research division, operating inside one of the largest corporations on Earth, may be sitting on a technology with a dual-use potential to revolutionize medicine and materials science on one hand and unravel the global architecture of digital secrecy on the other, all while its own lead scientist openly speculates that the machine might be drawing on computational resources from realities outside our own. That is not a sentence that belongs in a typical technology news cycle. That is a sentence that belongs in the kind of briefing document intelligence analysts write when they are trying to convince skeptical superiors that a slow-moving story deserves urgent attention before it becomes impossible to manage. So, where does this actually leave us, sitting here, watching this unfold from the outside? Willow is real. The below-threshold error correction is real, independently scrutinized, and published in one of the most rigorously peer-reviewed journals in existence. The Quantum Echoes result, with its 13,000 times speed advantage over the best classical supercomputer on the planet, is real and, crucially, verifiable. A word that finally separates this moment from the contested hype of 2019. The neutral atom expansion in March 2026 is real, a clear signal that Google is not slowing down, not hedging downward, but doubling its technological bets in parallel. The UK partnership is real. The market surge is real. Hartmut-Nevin's multiverse comments are real, on the record, made by a man whose entire career has been built on credibility inside the most rigorous scientific discipline in human history. What is not yet real, what remains genuinely uncertain, is everything that depends on what happens between now and that 2029 horizon Google itself has set. Will the error rates fall far enough, fast enough, to unlock the kind of large-scale algorithms that could actually reshape medicine, energy, and global finance the way the most optimistic voices are already promising? Will the post-quantum encryption rollout outrun the quantum hardware racing to break it? Or will some nation, some agency, some actor we have not yet identified, find itself holding the master key before the rest of the world has finished changing the locks? Will the strange whispers about parallel universes remain a colorful footnote in physics history? Or will future experiments push that idea from speculation into something closer to confirmed fact, forcing humanity to confront the possibility that every choice we have ever made has been quietly branching into versions of reality we will never see, never touch, and never know existed? Nobody currently has confident answers to any of those questions, including, by their own public statements, the scientists building the machine at the center of all of it. What we do know is that a chip the size of a coin, built behind closed doors in Santa Barbara, has already forced some of the most credentialed minds in physics to say things out loud that 5 years ago would have ended a career rather than made headlines. We know that governments are quietly racing to defend secrets that may already be obsolete. We know that a handful of vetted partners currently hold access to a technology capable of reshaping medicine, energy, finance, and national security all at once, and that the rest of the world is, for now, simply watching from outside the glass. The official roadmap says 2 milestones remain. The official timeline points to 2029. But roadmaps assume the world stays patient, and history rarely accommodates that kind of patience when this much power is sitting this close to being unlocked. Somewhere between now and whatever comes next, a line will be crossed. A line between a fascinating research milestone and a fully operational capability nobody fully knows how to contain. Nobody outside a small circle of researchers and intelligence analysts can say with certainty how close that line actually is, or who will be standing closest to it when it finally gets crossed. And perhaps that is the most unsettling part of this entire story. Not the multiverse, not the encryption cliff, not the black holes or the molecular rulers, but the simple, quiet fact that the most consequential machine currently being built on this planet is operating almost entirely outside public view, its true capabilities understood by only a handful of people. Its ultimate implications, still, even to them, an open question.